This is CPE 233. This is part of Lecture 1, which is a description of Experiment 1E. So Experiment 1 has many parts to it. We'll be doing Part E in this quarter. So Part E is essentially, there's a ROM that has numbers in it, unsigned binary numbers, or actually 8-bit unsigned binary numbers. You're going to evaluate each of those numbers. If those numbers are a prime number, you're going to write them to a RAM. Eventually, once you step through all the numbers in the ROM, you are going to essentially just continuously display the prime numbers that you found. There is a 2-number mode on the universal 7-segment display. That's what you're going to use here. Additionally, you have an LED that blinks. Essentially, the LED is blinking when you're searching the ROM, checking the prime numbers. Otherwise, it's continuously on. So, a couple constraints in here. Number one, a lot of these modules are provided for you. The digital modules are provided. Use those. And a lot of them have parameters in them. And I want you to override the parameters in the instantiation. I don't want you to change the models themselves. There's also a ROM module and an associated .mem file on Canvas. .mem is a special file in Vivado that you'll see when you add it to your project that it goes in a special place. You need both the ROM module and a RAM and the .mem file to read from it. If you take a look at the ROM Verilog model, you'll see exactly what's going on. Once again, these are available on Canvas. So this is using the universal 7-segment display device, which has a 2-number mode. That's the mode you're going to use. There's also a provided prime number checker module, which we'll talk about later. You're going to use that also. This is a circuit that's controlled by a state machine. And so the constraints here, I want you to use the template I provided as a starting point. Don't write your own. Don't write more than 10 states in it. Simply, this is very, very straightforward. Should be able to do it 4 or 5 states. I don't want any extra memory inside your state machine other than the state variables. Don't use math operators anywhere in your experiment except in modules like the RCA or the counters. Additionally, the ROM, essentially this FSM should be independent of the ROM and RAM sizes. So the approach to doing any digital circuit is this. First, you understand the problem. Once you understand the problem, you'll be able to see which modules you need for the circuit, and you're going to select those modules and plop them down. Once you plop them down, you're going to establish the data paths through these things, essentially the path that the data has to follow to make the circuit work properly. Once you do all this, you are going to control the circuit with the state machine, so you're going to generate a state diagram. Now, the state diagram has status. It's going to have status inputs to read the status of what's going on in the circuit, and then it's going to have control outputs, which essentially is controlling the various modules in the circuit. Once you do this, you're going to translate this to a Verilog model using a template, and finally, you're going to implement it in hardware. So once again, to understand the problem, by all means, don't wing it. Design it on a piece of paper first. Keep it as simple as possible. Don't try to do anything clever. Like I always say, my motto is make it work and then make it work good. Generally in this class, we only have time to make it work. So the design process itself is iterative, which means that you're going to make mistakes and you're going to have to go back and fix them. It's not like a linear such that you start and then you end and it works. You're going to have to fix your mistakes. So this whole design is modeled with Verilog, of course, and implemented on the Basis 3 board. You're going to have to use the simulator unless you're, way better than I am. I had to use the simulator to get this working. So if you've got questions, send them to me. By all means, send me your diagram. Send me questions like, will this work? And I'll gladly answer them. So this is your top level circuit, and you can see it has the stuff that's used to drive the 7-segment display, and then there's your blinking LED. The only inputs are a button which starts the process and a clock signal. This is the prime number checker device, and it has a couple interesting inputs here. You've got, and we'll look at the associated state diagram in a second here. You got to start the thing. It has a test mode, which essentially the test mode is when you insert this input, it bypasses the internal clock dividers, which is essentially used for simulation. So once again, to put it, when you're simulating, you got to put it in test mode by asserting this input. This is the number that it's checking to see whether it's prime or not. When it is finished checking whether it's prime or not, it asserts this done input. At that time, if the number is prime, it will also assert the prime output. Now, if the prime output is not asserted when the done input is asserted, then it wasn't a prime number. So this is a basic timing diagram right here. You essentially send the start input a pulse, and that starts the process. Then there's going to be a little bit of time delay here. And for this example right here, this is an example where it completes the process by asserting the done, but then the number itself that it was checking is also prime, so it turns the prime output on as well. It asserts the prime output. So this is the same diagram essentially on this part, but this diagram was starting from a non-prime number. This diagram here is starting from a prime number. And what you see here is that when the process starts, the done turns off and the prime number clears also. So the result of this process is the done asserts, but the prime number doesn't assert. So whatever number was on this input for this cycle here, it wasn't a prime number. So it is optional a couple things are optional to display the number that you're checking on the 7-segment display as you're looking for the numbers. I think this helps with visually debugging the circuit. You don't have to do this if you don't want to. You're going to have to use the simulator in this one. I mean, practically assured that you're going to have to. The idea is you're going to have two modules in there that have testing inputs. Now these modules are modules that have clock dividers. They are a clock divider or they have clock dividers, and the idea is you have to put it in test mode to be able to simulate it. And so I put this little hint down here as far as using this parameter value for both of the test inputs. One of the test inputs is going to be on the clock divider module. The other test input is going to be on the prime number checker module. So essentially what you need to do is set this parameter to 0, make this test input the input to the test inputs on those two modules. And the idea here is if test is that input, you only have to change this variable right here to put it in test mode. So test mode would be a 1, a non-test mode would be a 0. Non-test mode means you're actually implementing it on the board. And so that's all, folks. By all means, if you have questions, ask them.